Proving triangles similar. So our essential question is, how can you prove triangles are similar? Okay, and I basically just did a summary that will help us. So there are 3 triangle similarity theorems, and this is how you know whether or not triangles are similar. So the first one is the angle-angle similarity theorem. And basically all you need is 2 angles of one triangle congruent to 2 angles of the other triangle. And then you know that they are similar. And basically that's because if these 2 angles are congruent to these 2 angles, they all have to add up to 180, right, in each triangle. So these last angles are also going to be congruent, which means you have all 3 angles congruent to all 3 angles. But as long as you know that 2 of them, so these 2 angles and those 2 angles are congruent, then you know that you have similar triangles. Okay, the other one is the side-side-side similarity theorem. So the side-side-side similarity theorem basically says if you can set up a proportion where all corresponding sides are proportional, right? So all 3 sides. So I got AB corresponding to DE, right? So that ratio. And then BC over EF, that ratio. And then AC over DF, and all 3 of those ratios are equal, then you know that you have similar triangles. And the last one is the side-angle-side similarity theorem. So if I know that one pair of angles is congruent, and I also know that I have 2 sides proportional, then I know that the 2 triangles are going to be similar. Okay, so here you need 2 congruent angles in both triangles. Okay. Here you need all sides are proportional. And here you need 2 sides proportional and a congruent angle. So 1 congruent angle, 2 sides proportional. So let's use these to do our examples. All right, so for the first one, use the AA similarity theorem. So 2 angles need to be congruent. All right, so determine whether the triangles are similar. If they are, write a similarity statement. Right, similarity statement looks like that. And explain your reasoning. Okay, well, let's see what we got here. First of all, I don't see any, oh, I do. I see angle R is congruent to angle X. So angle R is congruent to angle X. Okay, I'm going to need 2 angles that are congruent, though. Okay, so far I just see these 2. So I'm imagining those 2 are corresponding. Let's find the missing pairs of angles. So altogether, these have to add up to 180, right? So I know that 21 plus 99 plus this angle Y have to equal 180. Well, 99 and 21 is 120. So Y, if I subtract 120 from both sides, Y will equal 60 degrees. Well, notice I needed that angle to be 61, I believe. Let's see what angle S is. Okay, so let's come over here. So 61 plus 21 plus S equals 180. So that's going to be 82 plus S equals 180. Subtract 82 from both sides, and I get the fact that S is equal to 98. So I don't think, if this is 98, there's really only one pair of congruent sides here. Okay, so we know that angle R is congruent to angle X. However, the measure of angle y is 60 degrees, which does not equal the measure of angle t. Which does not equal the measure of angle t. And we also know the measure of angle s is equal to 98 degrees, which does not equal the measure of angle z. So the triangles cannot be similar because there's only one pair of congruent corresponding angles. Let's go back. So, determine whether the triangles are similar. Well, I said that the triangles are not similar. If they are, write a similarity statement and explain your reasoning. Okay, so I didn't have to write a similarity statement, but I did have to explain my reasoning. So I would say all of this is a very thorough answer. Full credit there. Move on to the next page. Okay, we have to show that triangle QPR is similar to triangle QTP using the angle-angle similarity theorem. Now, they're not always going to tell you when to use which theorem, so you kind of have to be a little bit familiar with all the theorems. Not a little bit, a lot. Let's see, I'm going to use some colors here. So, okay, two triangles, QPR. So QPR is this bigger triangle out here. I struggle with these a little bit, so I like to really make sure I get my corresponding angles in the right positions. And QTP is this smaller triangle. So I'll highlight that one with yellow. Okay, QPR. Well, P is the angle that corresponds to angle T. So right now, this QTP triangle is in a strange position for me. So I'm going to put it so that my corresponding angles are in the same positions. So I'm going to rotate QTP so that T is down here in the bottom left-hand corner, just like P is, because those are corresponding angles. So I'll just draw myself a rotated QTP. So T is now down here. Oops. And basically what I've done, let's see, so Q should still go with Q. So Q needs to continue to stay where it is. P goes with T, P goes with T, all right, and then R goes with P. So R is down here, so now P is here. So actually what I've done is I've taken this, I haven't just rotated it, I've actually flipped it, right? I've reflected it so that QT is lined up with QT here, okay? All right, doesn't look perfect, but it's close enough, and it gives me an idea of where my corresponding angles are, or my congruent angles should be. So the fact that these guys are similar tells me that, well, angle Q is definitely going to be congruent to angle Q. Okay, so I know that angle Q is congruent to angle Q. Okay, let's see. I know that angle P is congruent to angle T. And that's because I have right angles. Here I know angle Q is congruent to angle Q because they're basically the same angle, right? I think that's enough. If I have two angles, right? This angle congruent to that angle. Angle P congruent to angle T, right? Because I rotated it and reflected it. Okay, so now I know that I have enough information to say that the two triangles are similar because of angle-angle similarity theorem. So I can say that triangle QPR is similar to triangle QTP because of angle-angle similarity. Right? That's enough to say that two triangles are similar because two of their angles are congruent. And I showed that both of those pairs of angles are congruent. Okay, example 3. Modeling with mathematics. A school flagpole casts a shadow that is 45 feet long. Okay, so I've got let's see, a flagpole here. Let's pretend like there's my flag. Okay, and it's going to cast a shadow. So when the sun shines down on it, right, that shadow that it's casting right here is 45 feet long. At the same time, a boy who is 5 feet 8 inches tall, okay, so we've got some students standing right here, and he also casts a shadow that is 51 inches long. So this is 51 inches, and he is 5 feet 8 inches. So let's see, this is a boy. What should I do here? How can I don't know. Let's just have him standing right next to it. How about that? Okay, so there's a shadow. Okay, his shadow is here. The sun's over here reflecting or doing basically casting these shadows. Okay, and his height, he was 5 feet 8 inches. So I'm going to write that here. How tall is the flagpole to the nearest foot? Okay. So I have a couple ways of doing this. Notice I've got different units though. Right, so this is in feet, this is in inches, this is in feet and inches. I think it's going to be easier if I just convert everything into inches. So that's what I'm going to do. And then I'll come back and I'll convert it back to feet. Okay, so to convert to inches, well, if I start with 45 feet, and I want that to be in inches, then I'm going to multiply by however many inches are in a foot. Well, there are 12 inches per foot. So what ends up happening here is the feet, those are units, those reduce, right? And this is 45 times 12. Gives me 540 inches. Maybe I'll just keep it with IN. All right, so this is really 540 inches. Now this guy, he's 5 feet 8 inches. So let's figure out 5 feet. How many inches is that? Well, that's 12 inches per 1 foot. The feet reduce. Once again, 5 times 12 is 60. So he's actually 68 inches, right? So this is actually 68 inches. And I think that's already in inches. Okay, so I'm going to use my inches to help me. Now, both of these, the flagpole and the kid, they're both standing at right angles, right? Let's pretend like everybody's standing straight up, okay? And the sun is also hitting them at the exact same angle as well, because the sun's up here, so it's hitting both of these at the exact same angle. So we also know that we have this angle congruent to that angle. Therefore, by angle-angle similarity theorem, I can conclude that these two triangles are similar. So to find a missing side, I can set up a proportion then, right? So maybe I'll do height versus shadow. So I can do height over shadow for both the flagpole and the boy. So the height of the flagpole is X. The shadow is 540 inches. The height of the boy is 68, whereas his length of his shadow is 51. Okay, so what I have here is I have a proportion now where I can cross multiply and I'll get my answer in inches. It's asking for the nearest foot, so I'll have to go back and convert that back into feet. Okay, so let's do, if I cross multiply this way, I'm going to get 51x And then this is going to be 68 times 540. Ooh, that's a big number. 36,720. Divide both sides by 51. I get 720. Now that's in inches. And I'm going to go ahead and convert that back into feet. So when I take 720 inches, and now I want to convert it into feet, well, I'm going to say how many feet per how many inches, right? I want the feet to be my final units. Well, I know there's 12 inches per 1 foot. Think of these as fractions. The inches now reduce. So multiplying, well, actually, let's see. Will 12 go into 720? I believe it does 60 times. So X is really 720 inches or 60 feet. So there's your final answer, 60 feet. How tall is the flagpole? It's 60 feet tall. Okay, and we use the height of this guy right here and his shadow length. And because the sun's hitting them at the same angle, we know that those shadows form similar right triangles. All right, so now let's use side-side similarity theorem. Okay, is either triangle PQR or triangle STU similar to triangle VWX? Okay, so VWX, we're going to set up a proportion where we test the sides of this with the sides of either this one or this one. And we're going to see if it's similar to either one. So how about I'll start with triangle PQR. So what I'm seeing here is that this is an isosceles triangle, right? So triangle VWX is an isosceles triangle. Well, so is triangle PQR. So really, if I had tested any of these two congruent sides with any of these two congruent sides, that's going to give me the same exact ratio. So what I'll do is I'll test like 8 and 12. So how about I'll do the smaller triangle first. Okay, I'll put that on top. So 8 is to 12, so 8 over 12, right? Because those are corresponding sides here. And then my bases are also corresponding. So I'll go the small one on top, so 12 over 16. So let's just test that. Now, I mean, truly, this should be side-side-side similarity theorem. So then I could also, say, oh, well, is this also proportional? Well, those are exactly the same thing. So I really just need to set up one set of ratios in my proportion and test that. Okay, so when I test this, I get, let's see, is that 144, 128, I believe. Let me double check that I did that math right. Yeah. Well, that doesn't work. Okay, so these two are not going to be similar because their sides are not proportional. So I'll say triangle PQR is not similar to triangle VWX because the sides are not proportional. I'll just abbreviate. All right. Let's try the next one. Let's try triangle STU. So same type of thing happening, right? Notice that this is also isosceles. So I'm really just going to have to test two pairs of corresponding sides. Okay, and why don't I go ahead and put the smaller one on top again. So we'll go 8 over 20 is equal to, and now we'll do the bases. So 12 over 30. Cross multiplying, I get 240 equals 240. So those sides are proportional, right? So we can say triangle PQR is similar to triangle STU because sides are proportional. Okay, so this is going to be the one that it's actually proportional or similar to. Now, these two examples come from section 8.3. Okay, using the side-side-side similarity theorem, we're going to find the value of x that makes triangle XYZ similar to triangle HJK. So notice now we're just going to throw a little bit more algebra in there. We've got some sides that have algebraic expressions, meaning that they have x's in them. Now you're going to want to be careful with this because you could set yourself up for something that you don't quite remember how to solve yet. In our next couple lessons, I am going to remind you of how to do some factoring and some crazy algebra from Algebra 1. So for now, let's try and keep this as simple as we possibly can. So let's see. I've got a missing side on xz. Okay, and x and z, corresponds with hk on the bigger triangle. Okay, so I know that if I set up like small over big, doesn't matter which way you go, it just stay consistent, then I would have x minus 5 over 30. That would be one of my ratios. Now let's choose another pair of corresponding sides. So let's see, maybe hj. hj corresponds with xy, which is 3. Okay, so hj is 15 and xy is 3, and I'm supposed to do the smaller over the bigger. So sometimes it's nice to write yourself, you know, how am I setting up my ratios? You could say, hey, I'm doing small over big. You could say I'm doing triangle XYZ over triangle HJK, just to make sure that, you know, your proportions, you have the small sides and then you have the bigger sides of the bigger triangle. Okay, so what was I saying again? So I'm going to do HJ and XY. Well, XY should go on top because I'm doing small. So 3 over 15. You can reduce this. I mean, it might be nice to reduce the 3/15. So x minus 5 over 30 equals 1/5. That way you're distributing something smaller. Okay, so when I cross multiply, on this side I'm going to have 30. And on this side, I'm going to have 5 times that quantity x minus 5. Okay, so let me come over here and keep doing the algebra. So we'll have 30 equals 5x minus 25. We'll add 25 to both sides. So we're going to have 55 equals 5x. Divide both sides by 5. We get x equals 11. Oops. So find the value of x that makes this statement true. I have found it. No further explanation needed. All right, example 3, we're going to use that side angle side similarity theorem. So the diagram is a scale drawing of a triangular roof truss. I don't know if you've ever been up in your attic, but if you've ever been up in your attic, you might see some of these trusses up there. And this is basically what they use to create your attic spaces in here, and then your roof goes along. And basically it's providing support and structure for your roof. Okay, the lengths of the two upper sides of the actual truss are 18 feet and 40 feet. Okay, the actual truss and the scale drawing both have an included angle of 110 degrees. Okay, so you've got this actual, this is just the scale, but you've got this actual roof truss that maybe you've also seen them like on the back of big trucks being hauled away. And this one's going to have 40 feet, 18 feet, and the angle in between is also going to be 110 degrees. Now, I put the 40 feet over here because the longer side is on the left-hand side. Okay, and then I put the 18 feet over here because this is the shorter side of the roof truss. I know my drawing doesn't look like it, but don't focus too much on my actual drawing. Focus on what you know. Okay, the actual truss and the scale drawing both have an included angle of 110. I already read that. Is the scale drawing of the truss similar to the actual truss? And explain. Okay, So there's a couple ways to do this. And in our problem that we did earlier, let's see this problem here. Notice how I was dealing with like feet and inches, and this one had feet and inches in it. So I had to go into one set of units because this set of units had two different units in it. Okay. What you could do is you could say to yourself, I'm always going to stick with like feet and inches. So I'm going to set up a proportion where it's feet over inches equals feet over inches. Or in other words, this is going to be the actual over the scale, right? That's what I'm going to do. So in this case, because these are both in feet, I can put them both up here, and I can put these, because these are both in inches, I can put them down here. I can do the cross multiplying, because now I'm going to have inches times feet equaling inches times feet. So those will be the same units, and I can check and make sure that the numbers work. Now, if that makes you feel uncomfortable, change these to inches, or change these to feet. But as long as I set up my proportion where the same units are in the same position, we're going to be fine. Okay. So how about I'll take this longer side. Okay, so I'll do the 40 feet. I'll use my units this time to kind of show you where they're all going. Over my longer side, right, in inches, equals my shorter side in feet over my shorter side in inches. And then if I cross multiply, I'll have 180 inches times feet. Okay, so inch foots equals, and then here, 240 inch foots. Now that's okay. I know that this looks like a weird unit. This is actually, I recently ran into this problem where I was dealing with torquing something, meaning like putting as much pressure as I could without breaking a part of my bike. And it was actually, I think it was in foot-pounds was the pressure I was supposed to be putting, and it ended up needing to be converted into inch-pounds. So there are these weird units out there that basically when you multiply certain things together, you get these strange units. That's okay. And notice how these are in the same exact units. It's totally fine. Now, these are not equal, right? So even if you got rid of the units, right, they're not equal. Okay? So I'm going to say that these are not proportional. So the scale drawing of the truss similar is not similar to the actual truss. Okay, so I'll say they are not similar because corresponding sides are not proportional. And I guarantee, had you gone through and converted these all to inches and set this up, you'd get the same exact fact that they're not proportional. And if you need to, you can go ahead and check that.